All right, all right. Let's start the second half of the lecture. Right. So in this lecture, we are going to keep talking about math. So we're going to talk about, accuracy estimation strategy. We are going to talk about hardware aware math, zero-shot math, and the new architecture hardware architecture so co-search, as well as some applications, how people using math for different applications, including near language, natural language processing, GAN and point cloud, post estimation, etc. All right. So let's continue to talk about the performance estimation. All right. So apparently the easiest way is train from scratch. Right. So I search one architecture, I use a data set, and I search from scratch. I got this network accuracy, and then I evaluate with the validation data set. Apparently, the problem with that is if you train from scratch for every child network, the cost is it's really prohibitive, right? So the original neural architecture search with reinforcement learning paper basically says, oh, I'm going to train from scratch for every network I sampled. With this approach, if you train a CMAR10 data set, you are going to need this many GPU hours. Okay, and you have a larger data set, so it becomes just impossible. All right. So then people start to think about, well, instead of training from scratch, can I treat a little bit, optimize the process. So inherit weight and height network are two approaches. So inherit weight, so this net to net accelerating learning via knowledge transfer. So what it means is that, well, if I have a network, and this network is already trained, that has all these weights, can I just simply replicate the weights to transform the network to make it wider? Similarly, if I already have the network already trained and has all the weights, can I just simply repeating part of the network to make it deeper? Okay, so this way I'm reusing all these weights just already got trained, right? So that's kind of the key idea. So this efficient architecture search paper in 2018. So basically, it wants to see how I can make the network wider and the deeper using the weight I already have. So I'm going to inherit the weights from a parent model to reduce the training costs instead of training from scratch. Generate network transformation action to update the model architecture instead of directly generating the model architecture. So this way, basically, this paper basically says, wow, I originally already have a network, and then I'm using the weight I already got somehow transform the network, see if I can have a better network with the same weight I already got. Okay, so apparently, like this way, this may not give you the, the optimal architecture, but there's a way to explore other possible designs quickly, right? So that's the idea. Another idea is this hyper network. So what this paper, this SMASH paper, this is one-shot model architecture search through hyper network. It's quite interesting. Essentially, you are going to have a so at each training step, a random model architecture is sampled from the search space. The hyper network generates the weight based on the model architecture. So for example, like let's say like this is a network, okay, and you are going to and code the network's node with certain embedding method. And then you are using this as input to a supernet, to a hypernet. And this network basically says, oh, if I see you just sampled a network architecture like this network is going to generate the weight for this sampled the child network. Does that make sense? So I have a network takes your network architecture as input and it generates the weight for all these connections. Okay, so that's the idea. Make sense? So and then well, once you have this child network and the weight I generated for you, right? And then you are going to test on the data set and see, well, if this, so basically this hyper network is assigning the weight for you, okay? And you are going to evaluate this child network to see if the accuracy is good. Then the interesting thing is, well, then if you think about it, if the loss function for this child network is not good, we can actually use that loss to train this hyper network. Because, well, if my child is not doing well, it means that I need to be updated as well. And we can use the same loss function to update myself. Does that make sense? So that's kind of the idea of this so-called hyper network. You are using a separate network to assigning the weights for you. So that's that. Then let's talk about this hardware aware analysis. So far, all the searches except the TinyML. So most of the search network, all these new architecture search paper we talk about, most of them only cares about the accuracy. We haven't really talked about this hardware awareness. Means that right now everything is hardware oblivious. I don't care what's running, right? What hardware you are running, that's the network I'm giving to you. Wrong direction. But we know that different hardware have very different characteristics. One model probably isn't the best for all. So we need to for each particular different hardware, we will need a different way of different network for specifically designed for that hardware. That would be the best way to achieve both accuracy and efficiency. So this proxyless NAS paper is kind of one of the paper that does that. So we talked about that, so what is, before we talk about this so-called proxyless NAS, we need to talk about what is proxy. So when I talk about, this reinforcement learning based new architecture search method, we know that, the training, if you have to train every child network from scratch, it takes much longer time. Not to mention if you want to do this for a larger data set, right? So what I end up people does is that instead of, when I have the child network, instead of train that child network on the target data set, let's say ImageNet, I'm using a smaller data set as a proxy task to evaluate my child network. Instead of train this network on the ImageNet, I'm going to train this image on a CIFAR-10 and see how good it is. So evaluating the child network CIFAR-10 is kind of the proxy to evaluate this network on the bigger ImageNet. So that's the idea, right? Or I'm going to instead of train the network until it really converges, I will just train fewer epochs and see if it's actually, for example, if it's if you are reducing the loss significantly, right? So you want to do that. Basically, you want to reduce the cost of doing this performance estimation, right? So that's the key idea of this proxy. So this paper says, well, all those proxy tasks still consumes too much of time. So they propose this so-called proxyless network. It says like, all the previous ones are expensive. This NASNet, to find a good network, even on C510, needs 5 years on a single GPU. This DARTS, this gradient descent-based differentiable NAS search is faster, but it still needs 100. What is 100 gigabit? It needs like 100 gigabytes of GPU memory to directly search on ImageNet. So how do we, so what does this proxyless NAS does? So it's a very, well, first of all, it follows the gradient descent method. So for the input and to the output, I have all these different options. I don't know which one to pick. So as I said, like we can assign a parameter alpha to each of these paths or each of these operations, right? And then like the output, of course, it equals to the sum of these doing this softmax of all these operations, right? You combine this together. And also like this network also adding another layer, which is this gating layer, this binary gate, essentially says, well, I'm going to just pick one of the paths, not two, not three. So I just pick one of the path. Okay. So first you are building this over parameterized network with all these candidates. You assign alpha, beta, gamma, and delta. And the training process is going to be just trained on this one super network. Okay, so you train this once. Okay, and also you are pruning the redundant path based on the architecture parameter, which is this alpha, beta, gamma, delta, and as well as this binary gating. So binarize the architecture parameter and allow only one path of activation to be active. So and every time in this proxy NAS, it's further reducing the computation cost by only allow one path of activation to be activated each time. Okay, so it's always a trade-off as the search time or like how many spaces you are searching, right? So it's trying to have a balance here. So the memory footprint is reduced from big O(n) to O1. And it says like, well, with this way, you can significantly reduce the computation time because you only train the network once, and even during the training, you only allow one activation path to be activated. Okay. So it says it's much faster, than reinforcement learning as well as the original DART. And also, like another thing, this paper says, well, if you're simply looking at the number of max, the number of operations, doesn't necessarily mean that it's fast. What does that mean? So far, we have been using the number of operations as a proxy of how fast or how efficient the network is. Means that, well, if we have, because the assumption is that if we have fewer number of operations, then the network is faster, right? Because that's our assumption. So this paper basically pointed out that that's not necessarily the case. Why? Why the number of operations does not equal to the actual latency when you are running the network on the hardware. Does that make sense? That make sense? So it shows this. So this mobile VNet has this 500 less than 600 megas, but the latency is over here. Okay, the other two network, it has a fewer max, but the latency is much higher. Well, I won't say much higher, but so let's say this is like 120-ish, this is 190, so it's much higher, right? So you have fewer number of operation, but it takes longer to run. How is that possible, right? Because that doesn't fit into our assumption. So what happens is that you have fewer max, but you have higher latency. So what the paper pointed out is that basically says, well, if you look at these two different networks, if you look at these two different networks, one network, I'm sorry. So so what this figure is trying to show is that this is the MAC, this is the latency. I see. So what this figure is trying to show that, well, if we have the same number of max, but these operations are in different places of the network. One network might have many layers, but each layer is small, so you end up have the same number of operands, right? The other network, you don't have a lot of layers, but the layer is big. The hidden layer's dimension is big. So in this way, you can have the same number of operations, but they are in different places. Does that make sense? Does that make sense? So, and this one is trying to show, like, if you run these two different networks, one is that like in one network, it's basically the network is wide but short. The other network is longer but thinner. Does that make sense? Then, if you run both networks on this GPU, you will find that this wider network, which means that the hidden layer's dimension is wide. Actually, the latency doesn't change at all when you are increasing the number of max. So if you keep basically says, well, if you just keep increasing the width of these hidden layers, the latency doesn't change. Even you are increasing the map, the latency doesn't change. Does that make sense? But if you are, if you are changing the number of layers, the latency. So basically now, let's say I have this network and I'm keep adding the extra ops into this network. If I'm adding these ops to the width of the layers, the latency doesn't increase. But I'm adding these ops into the layers of the network, the number of layers of network, the latency will increase. Does that make sense? So therefore, even though we are adding same like 100, so let's 100 mega max, the latency changed differently. Why? So the reason, well, the apparent reason, what do you think? Why?
Because it's like for if you add layers, then you have to wait for the first layer to complete to give the output to do the computation of layer 2.
So if you're adding to the number of layers, it's sequential, right? But if you're adding to the width of the network, they can be parallelized. And GPU is good at parallelizing, right? But then, like, if you think about it, if it were not a GPU, if it's just a CPU, what will happen, right? The characteristics will be different, right? That makes sense. So I think, do we have a? Is this a FPGA? So this is a Raspberry Pi. So this is a simple CPU kind of thing. So you can see that, well, for this CPU base, then if you are just keep making the network wider, then the latency actually will increase. See, so different hardware, because the way you are designing the hardware, then like it's affected differently by how you are designing the network. Make sense? So And you can see that while the GPU is not affected by the width at all, which is the hidden dimension, right? The hidden is the width of the network. It is not affecting at all, but the CPU is affected dramatically because the CPU cannot parallelize them. Okay. The takeaway is that we can't simply using the number of ops as a proxy for the actual latency when it's running on the hardware. Make sense? So so this paper basically says, well, if we can just use the number of ops, what you can do is that like I'm just going to build a table. I'm going to measure the latency for some basic blocks, like 3 by 3, 5 by 5. I just measure the latency and building a block, building a table. And every time I just do a table lookup for that basic block. Does that make sense? So I can have a table to do that. I can even have a latency model kind of, so just measure this and got this table. And then every time I got the architecture, I'm going to just look at the table, got the latency. Yeah. So they find out the look table actually gives you fairly good estimation of the actual latency. So this one says, well, instead of using a table, can I train a network to estimate the latency? Right. So that's what they did in this paper. So I have a network prediction network. I will take your network, your network designs, kernel size, width, and resolution, and all that hyperparameter as an input, and I train a network to predicting the latency. That's what they did. And also they share fairly good, performance on this predicting model. And what this is trying to show that, by doing this NAS for each particular hardware, the model is indeed faster than this non-specific counterpart on this mobile device. Okay, so they show that if you specifically train this network, search this network by taking the hardware into consideration, you can further reduce the latency. Okay. And this one, they did this on GPU, on CPU, on mobile phone, and all of them shows that, well, if you specifically search that for GPU, then GPU is going to be, that model is going to perform the best on GPU. Search for CPU, the model is this, and then if you specifically search for mobile, that's the latency. So that's going to be, so you can see that if I search for mobile, 78 is going to be lowest compare other two models. Okay. And they show you, so this one basically shows like, two architectures that they search for CPU and for the same task, same data set. And they find out, they search for CPU, that's the architecture. They search for the GPU, this is the architecture. So you can see that these two architectures are indeed different. Okay. So it's on the same data set. They search one for CPU, one for GPU, and they find out, they just compare the architecture of these two networks. See the architecture is different. So that's basically what they want to show. Then like he talks about how to improve the design productivity for diverse platform. Instead of search one network for each particular platform. So basically it says, well, now if I have a new hardware, I'm going to do this search process, everything from scratch. Then for this hardware, then I'm need to build up the latency table and do the search again, right? So that's this search, so-called search productivity. So what they want to do is that, well, can we just use a unified approach, just search one network and then tailor that network for each specific hardware. So these two approaches are different. So one approach is that for each hardware, I'm going to search one network, right? The other is I'm going to search one network. And it depends on what you are using. I'm just going to scoop a subnetwork from this big network and then see how good that is. Does that make sense? So this is their so-called like once for all paper. Well, this is basically says like if you do this for each particular hardware, it's going to be still going to be like really expensive. Okay. So instead of instead of train a network, get accurate latency for each hardware and repeat, I will just train one network, sparsely activated. So it's kind of like a parent network. And I will, every time if you are using a new hardware, I'm just going to, from this big parent network, I'm going to get a subnetwork and get the accuracy and the latency. And this way is going to, the search process is going to be much, you just do this once, right? So that's the idea. Okay, I think this one illustrates the idea. So this introduced this once for all paper, and they will just train one network and specialize it for efficient deployment. Okay, this is once for all. So this once for all network contains many child networks that are sparsely activated. Sparsely activated means that for each particular network, well, for each particular hardware, I may only need like one subset of those activation. That's all I need, right? So then like if you got a GPU, H100, I'm going to use this network. If you have a 4090 desktop kind of GPU, I have to use this. If you have like mobile GPU, I have this. Right? And then you have different hardware, you're going to use different network spaces. Even for based on what kind of battery condition, I can select a different network. So that's that. But the idea is actually fairly very simple. So what the main idea is that when I'm trying to scoop a subnetwork out of this parent network, the parent network should be very readily to be extracted, right? So easy to extract a subnetwork while maintaining the accuracy. So that's the idea. You don't want like you don't want to extract like subchild networks very differently because that can maintain the accuracy. So the idea is that for the kernels, it's like progressively shrinking the kernels. I'm going to train a network, with 7x7, 5x5, and 3x3. Okay, and then like it depends on how powerful your hardware is. I'm going to pick the corresponding kernel. Okay. Similarly, for the layers, also like I'm going to train a with full depth, as well as with the with all these bypass connections. These bypass connections. If like you have a smaller, less powerful hardware, then I'm just going to extract this part of the network out to make sure it's not affecting the accuracy too much, while still like make it runnable on your less powerful hardware. Does that make sense? Same thing for the number of channels. It compute a so-called channel importance. So the way that they are computing the channel importance is simply calculating the L1 norm of all these weights inside this channel. So basically, it's just sum all these the weights inside this channel together, see which one's bigger. If the weights are bigger, the sum of the weights are bigger, I think this channel is more important. Does that make sense? Then it's just sorting them, rank them from big to larger to small. And then like when you are trying to prune the network, when you are trying to shrink a network, prune the network, it'll always make sure that you got the top K highest important channels first and ditch the less important channels. That's how they are shrinking the network. Okay, so that's that. So in this way, they have this so-called like elastic resolution. They have this elastic kernel size. You can pick like each of them, one of them. You can have this elastic depth, and you can have this elastic width. So by doing this progressively, you can kind of train this super network and still get like just subset of the network to have a relatively good accuracy, but still like can run on a less powerful hardware. Okay, so that's the basic idea. So the once for all network design models has higher arithmetic intensity, means that it computes more. It becomes less memory bound, which is great because now computation is cheaper than the memory access. Higher utilization and perform without changing the RTL. So this one is it does this for this Xilinx FPGA. It compares the what is that? This is the giga operations per second. Giga operations per second. Compare this three different networks on this FPGA, and this one has higher arithmetic intensity. They show that like they try this on all these different hardware, and this red line is their performance. Okay, and basically they can push the parental front significantly compared with all these blue lines. Okay, so that's this so-called hardware awareness. Okay, next let's talk about the zero sharpness. So zero sharpness is that I want to estimate the accuracy without training it. So which is quite interesting, right? How do you estimate how good a network is without even training it? So I think that the idea here is actually really interesting. So there are two papers, one's called ZenNAS and one called GrabNAS. Let's see what they are. So the idea is that I don't want to train it at all. Okay. So let's see what's the idea of this zero shot, this is ZenNAS. So the key idea of ZenNAS is that, well, for any network, and for this network with a random assigned weight, the key idea is that if this network is a good network, then this network should be sensitive to perturbations. If a network, I don't know what the network's weight should be, okay? I don't have the weight, I haven't trained it, okay? But if this network were a good network, this architecture were a good network, it should be sensitive to input perturbation. What that means is that if you just change the network, the input a little bit, the network should be able to differentiate them. Does that make sense? So that's the key idea behind this. If it were a good network, then if I just change the network input a little bit, the output should be different. Means that, well, this network can differentiate very small change in the input. Does that make sense? So just base that key idea and let's see what it does. Okay, so it initializes a random input, okay, X. The input is random, follows the normal distribution. It added a small perturbation to the X and obtained an X prime. So now I have an image X and I have an image X prime basically. Okay. I initialize all the weights of the neural network to a normal distribution. So all the weights are randomly assigned. It's not the correct weight, it's just randomly assigned. I calculate the difference of the log between these two inputs, basically. And basically says, well, if it were a good model, it should be sensitive to the input. So the log difference should be big. So that's the key idea. It added some sensitivity to the batch normalization, but the key idea is this. So this is really interesting, right? So without even training it, I'm using one known rule to want to rule out all those bad network designs. Does that make sense? Okay. Okay. So the paper is here. If you want, all these ideas, if the details, look it up. But that's the key idea. You get the idea, right? The graph sign is similar. So basically, we want to base some observation or known knowledge to rule out all those bad architecture designs. Okay. So what this says, while a good network should have, let me read this. A good model should have denser sample-wise local minima. While in other words, the distance between two local minima should be smaller. So for example, this is for these two different let me see how to say this. So for this two sample distribution, the local minimum here, they should be close to each other. If it were, and so basically says that this network is better than this, because the local minimums are closer to each other. Okay, and if they were closer to each other, it means that the gradient of two different samples have the same, the gradient of the different samples should have the same sign. Means that the green region should be bigger. Does that make sense? And the reason that it says the distance between the local minimum points should be smaller is that if it is true that the distance between two local minimum are smaller, it means that for this whole network, for the network itself, the minimum should be flatter. Means that it's more stable. So, well, check out this paper. This is a very interesting read. So basically, based on that observation, then without even training it, I'm just testing some of this condition to see which network is better. Okay. So that's that. So that's zero-shot math. So finally, I want to talk about this neural hardware architecture code search. So far, we either assume we only care about the accuracy, or we assume we are using someone else's hardware, right? We are using mobile device, we are using GPU, we're using CPU, we are using Raspberry Pi. Okay. What if you have the freedom to design hardware? Like if you were having a FPGA, then you can actually design the accelerator, right? Or if you are a ASIC designer, you can design your own accelerator together with your network, right? So that's the idea of this neural hardware architecture code search. So both architecture search and accelerator architecture design are important to enable specialization acceleration. Traditionally, what we did is you design a network and you run it, you got feedback, and you just keep doing this iteration, right? What about we design them together? So that's the whole idea here. So for a accelerator, the parameters you want to design, including local buffer size, global buffer size, processing number of elements, the array size, the connections, right? For the network, of course, you want to design all these layers, channels, kernels, and all these. So this paper is trying to design them together. So let me go the next first, and then come back. So this is the big picture of this paper. It has this, this search process. In this paper, actually, you can see that this is using a evolutional based method to do this mutation and crossover to do the new architecture search. So once you searched it, you have a mapping algorithm to map this to a particular hardware. And in this hardware design space, it also has this, this way of designing this. And so the mapping algorithm is trying to map a particular design to a particular design and see how good that is. Okay, so it's doing this search of the network as well as the accelerator together and using the mapping algorithm to have this to evaluate. It's using this EDP, this energy delayed product, I think, energy delayed product to evaluate how good this design is. Okay, so it's fairly so that's from the higher level. And if you look at the lower level, for a network, if you want to, for the network, if you want to, end of the day, the network is just a bunch of nested loops, right? So you have this, all these batch size, output channel, input row, input column, kernel row, and kernel column, right? So you have all these parameters, and you just have a bunch of nested loops. That's what it is when you are doing the tensor operation. Okay. Then like from this lower level, what you really want to do is that, well, for all this nested layers, which of the operations should be the one that's put on the hardware? Because when we are doing this loop operation, all these loops, the layers, they can be exchanged, right? It doesn't affect the correctness of this nested loop. So when we talk about hardware and software co-design, really what we are trying to figure out is that which layer of computation should be put into the hardware, and which layers should be actually running on the software and keep calling the hardware. In other words, which two layers should be put the innermost and should be put into hardware, and all the rest that should be just software and keep calling this hardware. Does that make sense? Okay, so keep that in mind. So then, like, what the design basically says, well, how should I order all these loops? Which should be inside is the best. Okay, so it has this. Let me. So basically, the search algorithm need to know like how to order these loops. Who should be inside? Who should be outside? But this ordering operation is not something that algorithm can numerically search. Okay, So what this the smart part of this paper is that all this index-based encoding. What it does is that it assigns importance to all these different layers. This loop order in this parameter dimension. It assigns importance to these loop indexes. So to this R, S, C, Y, and all these loop indexes assign an importance value to these indexes. Okay, so and then what happens is that while it fixes the dimension position in the encoder vector and assigning importance to these dimensions, and then it just keep the optimizer just keep assigning different important possibilities of importance to these indexes. So for example, like this K index, I'm assigning a importance as 3, C as 5, Y prime as 2, and then I sort it. Once you sort it, what that means is that, well, now I think the C should be in the outside, S should be inside. Okay, so by converting this into a numerical searching process, the optimizer can just try to assign the different importance to these indexes and see which assignment gives you the best overall latency and delay. Right? Does that make sense? So by doing this assignment and this sorting, you can kind of optimize this thing. So by doing this, it's kind of like, so this is going to be the one possible assignment is this. So the outermost is C, the innermost is S. So you are ranking all these layers as in this order. So C, R, X, K, Y, and S. Okay. So by just converting this kind of index ordering problem to a weight assigning problem, is can do this search. So that's the taker. So comparing searching the architecture slicing only, searching the connectivity and the mapping strategy as well as achieves considerable the energy delay product reduction. Oh, and then it shows like the architecture that this search find out the automatic search process, the NS, define the data flow, parallelize the output weight and output channel dimension, which is very different from existing human design. So that kind of just talk about this new architecture and hardware architecture code search. And now we just went through some of these, different how they are using NAS for different operations. So once for all, they use this for natural language processing. They evaluate this and see it's giving you a smaller latency, smaller model. Okay, they have this paper doing this new architecture search for point cloud, and also using this evolutional architecture search for point cloud. So give you this, better frame per second. This any cost again, I think I briefly mentioned in our introduction. It's using this NAS process, this train one super network, and try to carve out smaller subnets for this generative GAN, so that it enables you to do this GAN operation on even a mobile laptop. So this one says like they did this using the NAS, this paper using NAS to do this post estimation. Okay, and this one is they just show how they can do this face recognition, gaze estimation on Raspberry Pi and on-device segmentation and all the applications. They did for some quantum network. This is Flextron. It's I think it's a newer paper, 2024 paper. Basically, it did this similar idea that it's train a super network for transformers for large language model, so that you can carve out smaller pieces to mobile devices. So train one model, get many. Okay, so that's so for this lecture, we talked about performance estimation for NAS. We talked about hardware aware NAS. We talked about zero-shot NAS. We talked about zero new hardware architecture code search. We talked about some of these NAS applications. So a lot of these techniques, I just some of them I just kind of give you a very high level overview. If you are interested in the details, we all have all these papers listed, and feel free to check that out. Okay, all right. So that's all for today's lecture. All right, thank you. See you next week. So lab 2 is ready. Yeah.